All right. Thank you, everybody, for coming. I think we can start. So, my name is Sebastian, and I work as a lead consultant at Infusion Development, which is a consulting company. And for the last year and a half, I was working for one client and leading few projects for insurance company, basically. And I'm also Star Trek addict. So come by after the presentation if you want to talk about it too, not only about the virtual actors. Now, I'll be talking today about virtual actors, but I will start with 5 minutes or maybe 10 minutes introduction to actor model, just to create a stage for the discussion about virtual actors. And just out of curiosity, how many of you actually know the idea of actor model? Nice, quite a few people. Awesome. I will be also talking about Orleans, which I use for a reference as an example, because it was the first framework which was created for this idea. But there are other frameworks for different platforms, like for JVM. So if you're more into JVM, stay tuned. I will mention an option for you. So the goal of this presentation is basically to make you acquainted with the idea of virtual actors, so that in the future, if you're choosing the flavor of actor model for your project, you can make more informed decision. The other angle is that if you tried actor model in the past, but you find it unapproachable, you may want to try again, but maybe this time with virtual actors. So when I talk about actor model, I like to start with definition of object-oriented programming, something that everybody knows, and the definition of actor model. And the definition for object-oriented programming was formulated like in 1980s by Alan Key. And the first rule is that everything is an object. Simple enough. Objects have their own memory, and objects communicate by sending and receiving messages. So the definition is not specifying if this communication is asynchronous or synchronous. It's just we as industry, we choose to select a synchronous communication for objects, but it's not in definition. The last rule says that every object is an instance of a class. And there are like few other rules which were added later as a reflection on design principles behind Smalltalk, but they are not so relevant here. Now, also notice that there's nothing about inheritance or polymorphism here in this definition from 1980s, in original definition. When it comes to actor model, the definition was created by Carl Hewitt, who is responsible for a lot of research around actor model. And in his definition, in actor model, everything is an actor. Actors have their own memory, and actors communicate by asynchronously sending and receiving messages. So as you can see, the definition is quite similar, only difference is that we explicitly say that the communication is asynchronous. There are some additional rules. So actors respond to messages in 3 ways. They can send a finite number of messages to other actors. Then they can create a finite number of actors, and they can change their behavior, which means basically that they change the way they will respond to the next message. Or, in most cases, they will basically change their internal state. And the last rule says that actors process only one message at the time. So we can think about actors like about small, lightweight processes which process messages from the inbox one after another. So like one threaded process. OK, now let's talk a little bit about the communication. So as I mentioned, in actor model, the communication is asynchronous and via message passing, which implies that each actor has an address because I need to know to whom I'm sending the message. And you can obtain this address by when you create another actor. It's the same as with objects. When you create an object, you get reference to it, right? You can also get the address in a message. So one actor may send a message to another one saying, hey, process this data for me, but by the way, reply to this other guy, and here's an address. And the last way you can obtain basically address for actor is to retrieve it from some commonly accessible store. So sometimes in your system you have these very special actors that you want all other actors to have access to. So basically they will get this address from the from some registry. And obviously addresses must be globally unique because we cannot have ambiguous addresses. Now, so you have your system. There's a number of actors in there that communicate. So let's see what's the life cycle of single actor. So obviously, if you want to use an actor and send a message to it, you or someone else have to first create this actor. Then the became operation is actually just changing behavior. Actor changes its behavior. I don't like this term. It occurs all over the papers about actor model, but this term is better for actors which actually behave like state machines. But anyway, it just means that the actor changes behavior. Actor can crash. It's processing a poisoned message, or there is a hardware failure. It crashes. It disappears from the memory, or it's basically not needed anymore, and you remove it from the memory. Now let's think what's happening if your actor crashes. You have your system. It's running. Number of actors crashed. And your system basically cannot work properly in such a case, right? So what we do, we are trying to make actors reliable. And we do it by introducing special kind of actors. We call them supervisors. And the only role for the supervisor is to look at, link with another actor and watch him and detect if this actor crashes. So if this actor crashed, supervisor will detect it, recreate it, and then link with it again. So that if in your system, because of some transient problem, there's a number of actors which died, supervisor will make sure that your system basically heals to full functionality. There's always, and there's a little bit more to it in classic actor platforms. There are different strategies how you can supervise number of worker actors, but you can check this out in any publication about actor model. There's always a question, who watches the watchman? So in practice, we actually build the whole trees of the supervisors. So for example, if I, as a supervisor, supervise a few worker actors, and I see that they fail, and I keep restarting them, but they keep failing, I may decide that I will escalate the issue to my supervisor because I don't know what's going on. Maybe there's a non-transient hardware issue. Now, my supervisor may decide to restart entire subtree, or if it cannot, it will escalate even further the issue. And this tree can go as high as to the level of the system. So at some point, your entire application can restart. Obviously, one actor is no actor. So it would be very bizarre system which is composed only of one actor. So they come in systems. And at some point, you won't be able to put all these actors on one machine. There will be too much of them. So what we do, we distribute them and put them on multiple machines. And from the developer point of view, if we distribute actors, not much is changing. Because notice that because the communication is asynchronous, basically every call you make assumes that this is a remote call, right? So even if you distribute it, it doesn't change anything for you. Maybe you should test your system under stress on multiple machines, but code will not change. And then there are other ideas like this, for example, .NET remoting and remote objects, and basically no one is, I hope, no one is actually using it anymore. And the difference is that these technologies, they were trying to impose programming model where you assume like every call looks like a local call. So the programmers are not thinking about the issues when you actually distribute it, and there's additional latency. So the challenges of a classic actor platforms are that basically you have to manage actor lifecycle yourself. You create these actors, you watch them, and you restart them if they fail. You remove them from the memory if you don't need them anymore. And also, you have to manage the placement of actors. So basically, distributed resource management is on you. You have to decide how you spread your actors between multiple machines. And don't take me wrong, there's absolutely nothing wrong with these activities. It's always nice to have this fine-grained control over what's going on in your system. The only issue is that at some point, you start making the same decision over and over again. So in each project, you basically build your supervision trees and you follow certain patterns. So people at Microsoft, they acknowledged that, and they were trying to create a actor platform which simplifies basically distributed systems, which allows non-expert people to create services which are efficient, reliable, and scalable. And before I move on to the definition of virtual actors, I want to share with you what were the principles driving the design of the virtual actors platform. So the first priority for them was to simplify distributed computing. And the second priority was to empower experienced users. So you can translate these two statements to the statement where you say, well, by default, I will make decision which makes sense for the most of the cases, and that I will allow fine-tuning for the edge cases. OK, so what are these virtual actors? So virtual actors, as opposed to the classic actor model, they always exist, logically. For you, for your application, they always exist. And they are always addressable. They will be automatically instantiated for you by the runtime, but you will never know if this actor was actually instantiated or it was already in the memory. And their location is transparent to application, which is true for most of the actor platforms, if not all of them. But the statement is actually much stronger than it seems. It means that if I send a message to an actor, and in the meantime, runtime decides to move this actor from one machine to the other, I should be still guaranteed that the message will be delivered, although when the message was in transit, the actor was migrated from one node to another. So it's up to the runtime to make sure that all the messages are delivered. So all these characteristics, they basically simplify programming model. And in effect, all low-level operations are pushed to the runtime. And what developer does, he's basically focusing on domain modeling instead. So think about the virtual actors like about an infinite space of all actors that you could ever create in your system. Okay? And you see like on this picture, the circle depicts the actor, but some of them are like dotted. Obviously, you cannot fit infinite number of actors in memory. So what you do, you put in the memory only those actors with which you communicate now or communicated recently. Well, why would you care to build such a peculiar platform for this peculiar idea? So let's see. Let's go through a few examples. Let's say we send the first message to an actor. It doesn't exist, so the runtime will instantiate it, put it in a memory, and then deliver the message. If you try to send second message to the same actor, basically it's in memory, so the runtime just delivers the message. If the actor is not used for a defined time, the runtime may decide to deactivate it, remove it from the memory. And we may decide at this point that, well, my actor has a state, so I will persist this state to the disk. Okay? So next time, if I want to send a message to an inactive actor, runtime will realize that, create it. It will check if there is a state for this actor. If there is, it will read the state, put it in the memory, and deliver the message. So you can see in all of these examples, I didn't have to create or even check if the actor exists. I just send the message. I just assume it's there. Now, what's happening if you send a message to an actor which crashed when it was processing the last message? So again, runtime detects that, initiate the actor. If there's a state saved for this actor, it will read it automatically for you. And it will be the state, the last checkpoint before the failure. And then it will deliver the message. In all these examples, I didn't tell you where this actor actually is, if it's on the same machine or on a different machine, right? It's not up to me to know where it is. And if you look at these examples and you try to segregate responsibilities, you will see that the runtime is responsible for managing actor lifecycle. It creates it, deactivates them, activates them. It's managing failures. So if the actor fails, it will recreate it. And it also is managing actor placement. So basically, the runtime decides where to put given actor, on which node. So on the developer side, basically, developer is concerned with domain modeling, defining actors, defining their state, managing their state, and orchestrating interactions between actors. So you can see that the virtual actors is kind of like higher level abstraction over actor model. Number of low-level operations is pushed to runtime, leaving developer with this abstraction. An abstraction can work for you or against you. And in this case, I think this abstraction works for the developer because it segregates the code which is concerned with the domain from the code which is concerned with the infrastructure which provides us reliability, scalability, and efficiency. So in your team, you can have a number of awesome developers who are not afraid of any domain, obviously with exception of holy domain of cargo shipping. And if you need fine-tune certain areas in your system, you basically hire distributed system ninja who knows what he's doing, and he will be concerned with the fine-tuning the runtime and all the edge cases. Now, to reinforce this statement, I will show you some work which was done on a service which is written in Orleans and it's already on production. So this work was done by a group of researchers and the paper was published like this April. And they took a Halo 4 presence service. And the responsibility of this service is track which players are joining which games, and basically players are updating the game with statistics, and the game is sharing statistics with other players. And what they did is they didn't change like domain part. It was already there. They looked at the communication graph, which shows at any given time which actors talk with which other actors. And they noticed that at any given time, for this particular service at least, there were groups of actors that talk with each other a lot. So there were players in one game. But the groups don't talk too much with each other. So they formulated the problem as a graph problem, and then they tried to solve this graph problem. So they came up with ActOp, which is optimized placement strategy. It automatically detects the actors which frequently talk with each other and migrates them to, transparently to application, of course, to one node, so that less of the messages is actually remote messages. And to do so, they created scalable, distributed graph partitioning algorithm, which is quite interesting because it's not relying on one server to know entire communication graph, and yet it allows runtime to efficiently migrate actors and optimize the communication. Now, the only comment I can provide you here is, what? I think you will agree with me that not every developer can jump in and do this kind of work, right? It's more job for basically distributed system specialists and researchers. Okay. So let's talk about Orleans. So the Orleans was the first framework which was created for this idea. And I say that it basically extends functionality of traditional actor systems like Akka or Erlang OTP. And I say that because it has all the nice features that the other platforms have, like, you can send a message, actor can send a message to itself in the future, and if the actor fails in the meantime, the runtime will just recreate it in time to receive this message. You can process streams and queues, which are in Orleans also virtual, so it's also an interesting idea. You have client observers, which are special kind of actors, which are able to basically update client with changes without requiring client to actually pull for the actor state. It has very simple yet powerful persistence system. So it's something similar to Akka persistence. It works in a bit different way, but provides the same facilities. So if your actors are stateful, you can basically persist their state. So even if the node shuts down and starts again, you can read the state. But it also provides you this nice abstraction where runtime manages the lifecycle of the actors. It handles the software and hardware failures for you, and is concerned with the placement and balancing the actors between multiple machines. It also have a nice feature in which you can hint the runtime that this actor is stateless. So the runtime may decide to actually create multiple versions of this actor and distribute work between all these instances. And we call them reentrant grains in Orleans, because in Orleans, we don't use a term actor, we say grain instead, but it's basically the same. And I was telling you that the runtime is making assumptions for you, which cover most of the cases. So let's see what are these assumptions. So first of all, all communication in Orleans by default is following a request-response pattern. So basically, you send a message to another actor, and you wait for the reply. It doesn't mean that you block the thread. It just means that you will always wait for some kind of reply. If you want to do the fire and forget, create fire and forget call, you can do that. It's, for example, default in Erlang. In Erlang, if you want to do a request response, you basically have to use some facilities from OTP to accomplish that. So we have two lines here. The first line is just basically getting the reference to an actor. And the second line is what it does, it basically sends the message to the account actor saying, hey, give me your balance. And then creates a promise which will be fulfilled when the response comes back. What's interesting, by default, all this kind of communication have a timeout. So if the response does not come back in defined time, there will be exception thrown here, timeout exception, and you basically have to either handle it or escalate the problem to the previous guy and maybe roll back the entire, fail entire request. The other assumption is that the runtime does not ask you where to put actors. In Orleans, by default placement strategy, by the way, is random. Every time there's an actor which has to be put in the memory, the runtime will select a random node. It's random, but it's balanced, so you won't end up with one server which has a lot of them and one server which does nothing. As I mentioned, all the messages have timeouts by default. And the Orleans ensures isolation between actors by making all messages immutable. Basically, it copies the message before the message is sent. Even if the message is sent within the same node. So to accomplish that, the researchers, they realized that basically serializers, which are built in .NET framework, are too slow to actually do such work. Like the whole framework was too slow because of the serializers. So they spent quite a lot of time, and they came up with idea where they basically generate the serializers when you build your project. So when you build your project, basically the build tool will go through the all interfaces that you defined for the all actors and generate specialized serializers for each message that you could ever send there. And they are really fast. So among others, this is the reason why Orleans is so fast, although the actors are placed randomly. Now, I'm telling you a lot about Orleans that, well, you can simply create a distributed system, but it won't be worth much if it's not performant, if it's not efficient, right? So I have two graphs here, and I took them from the original virtual actors paper. And they show the performance of the Halo 4 presence service in function. So the performance is measured in, as number of requests per second, and it's in the function of number of servers in the cluster. And as you can see, when you go from 25 servers in the cluster to 125 servers in the cluster, the throughput scales linearly. I think it's like a holy grail of designers of distributed systems to have this kind of linear scalability, predictable scalability. Okay. On the other graph, we see the throughput in function of number of actors which are on one node. And as you can see, the throughput is almost the same if you scale the number of actors from 2,000 to 2 million. And there is a slope at the end, which is explained by researchers by some internal data structure in the runtime, which grows with the number of actors, but still these are pretty nice numbers. Okay, I want you to leave you with a full story, because maybe creating the system, the service, it's not difficult, but still you work with a distributed system, so you have to know certain things. The first thing is that at least Orleans was built to be available and partition tolerant, which means that if you have a network partition in your cluster, nodes have up to, I think by default, 60 minutes to notice that other nodes are not available, and then to decide on the new membership. If you are in a split brain situation and there is a cluster on both sides of the partition, you can end up actually with two clusters which are both available. So on both sides of partition, there can be the same actor initiated. If the network partition is gone and all the nodes connect again, the runtime will decide which nodes to restart and which versions of basically duplicated actors to kill. So you may basically end up with the system which is for a certain amount of time inconsistent. The second thing is missing delivery guarantees. So by default, Orleans will guarantee that it will deliver the message at most once, by default. If you use retries, which is a built-in feature, it will guarantee that the message will be delivered at least once, which means that you have to take care of duplicated messages in such case. Also, Orleans doesn't allow code hot swapping. So oftentimes when people talk about actor model, they say, well, it's really awesome because you can update a module while the system is running. And it's true for some platforms. For example, in Erlang, you can do that. But when I ask people who actually make money out of Erlang, they said, well, we don't actually use it. So I think maybe the usability of this feature is limited. Now, it doesn't support transactions in communication between multiple actors. So Akka supports transactions, but between actors on the same node. So again, this functionality probably is limited. I think it would be nice also to mention that Carl Hewitt, who is responsible for a lot of work around actor model, mentioned Orleans in his recent paper. And basically he said that Orleans and virtual actors is an important step in evolution of actor model. And it reinforces the idea that developers shouldn't be concerned with the low-level operations. So I think this note in this paper was really nice gesture for Orleans teams. Although I think Carl Hewitt actually worked at Microsoft Research at some point, so he probably told them that in person. So I have a few final thoughts. During my pursuit for understanding of actor model for the like 2 years. I read original papers from 1980s. I learned some Erlang. I tried Akka. I tried Orleans. And to be honest, at the beginning, I didn't really buy the promise of Orleans that it will make distributed systems simple. I was thinking, well, there were people and corporations which were claiming that, and I don't think anybody succeeded with that. So why do you think you can succeed? But when I dived into Orleans, I realized that it can be actually true. And it's because of these two priorities that they had. So first, simplify, cover most of the cases, make it simple for the average developer. And the second, empower the experienced user. So basically, if you need to fine-tune it, we will allow that. And also, I realized that the Orleans was created in the same research group as things like TPL, for example, famous task library for .NET, or async await feature, which is also in .NET and actually in C# itself. And these are very mature ideas that we use, like .NET developers use every day. And they built on this experience and created the Orleans. And also, I think important is the environment in which the whole idea and the platform was created. So it wasn't like there was a group of researchers who came together and tried to figure something nice out. At some point during the development of this framework, business came in and they said, well, we want to use it. And the Orleans team was like, I don't know, I don't think it's ready. But they use it anyway. And what they did is they started working together. And every idea that researchers were putting in the framework was quickly validated by the business. And the feedback was quite fast, right? And again, don't take me wrong here. I think Akka and Erlang OTP are wonderful products. And again, the only problem with them is that if you don't have suitable team, the whole project, the whole idea will backfire on you at some point. So if you want to hear some horror stories, say hello after the presentation. So what I want to, the main takeaway from this presentation for you is I think that if you consider using actor model, because you have a service which has to be responsive, it has to be reliable, always available, and it must be scalable, and you're considering to actually use architecture based on actor model, you should actually evaluate which flavor of actor model or which exactly technology you want to use. If you're from JVM environment, there's a clone of Orleans created by Electronics Arts. It's called Orbit. It follows the same programming model, the same ideas. It was recently open sourced on BSD license, and they use it on production internally at Electronics Arts. And the other thing is, like, if you find, for example, I find actor model unapproachable. It took me a lot of time to actually, dig into that. So if you find it unapproachable, but you want to, understand the idea, maybe you should start with the virtual actors and then maybe move to other platforms like Akka or Erlang. Now, as comes for resources, I think the most important one is the first one, which is the original virtual actors paper published by Microsoft Research. And it's quite approachable. You will for sure understand it. It's really nice because they explain what kind of problems they had, how they solved these problems, why they made certain decisions, and they also present the results based on the production services. The second one is explaining how the ActOp works. This is the algorithm for dynamic actor placement. And so it's half of the paper. The other half is about optimizing inter-node communication. It's also quite fascinating. Visit the third link if you want to check out Orbit. The actor thinking presentation is really nice for people who start with actor model. At least the first half of it is actually really nice, and I encourage you to actually check this out. Orleans and Akka actors comparison. This is an article written by Orleans teams and people from TypeSafe. So it's quite accurate. And it may help you understand what's the difference. What's the difference in approach at Orleans and in Akka, okay? And the last one is the Carl Hewitt paper where he mentions Orleans, but it's actually about, it is about actor model, but in context of Internet of Things. Okay, so this is all I have. You can find this slides on speaker deck, or if you have any questions later on, you can find me on Twitter. Now, I think we have 10 minutes for questions. Yes?
Yeah, well, it's not really related to, kind of it, but okay, let me ask it. So what do you think about using functional languages in actor model systems? Like, you know, for instance, Scala or F#?
Yep. So the question is, what do I think about using functional languages in actor systems? Like, for example, Akka is, I think the best way to use it is actually to use Scala, which is functional language. And Erlang in itself is a functional language, right? So, so myself, I am a big fan of functional languages, and yeah, if you're into it and you think you can, you know, basically build nice project with Akka, do it, definitely. The thing with the Orleans is actually, so the programming model, it's created in a way where they bridge the gap between actor model and this functional approach and the object-oriented world. So it's quite actually difficult to use it from F#. So most people will actually go and use C# instead. But I don't think like the decision shouldn't be made only based on that if it's functional language or not. Probably, yeah. Hey, another questions? Yep.
I would like to hear an advice. When would you choose to use actor model-based communication in a distributed system against message queue or service bus? When choose one or the other?
Okay. So I guess it depends on the background of your team. Oh, sorry. So thank you. So the question was, when would I advise communication as we see it in actor model, as opposed to using service bus and some kind of queues? So the only advice I can give you here is that probably it depends on the background of your team. Okay. And also, I have a feeling that if you have just queues and service bus, is not the only mean of communication that you will use. You will also use the normal communication between objects. So you will end up with parts of your system which are actually not so scalable. Okay, in the actor model, you basically assume that all the calls will be remote. So even if you distribute it, it does not hurt so much. And by the way, in Halo service, presence service, before they introduced ActOp, 90% of the messages were actually remote. And they still pulled off these really nice numbers there. So, another question? Did I answer your question, actually?
Yeah, I think I can.
Okay. All right, so if there's no more questions, thank you very much for your patience.